Today we're looking at how to find the area of a region that's made up of two or more parts. So we call this a combined region. And the area of combined regions can be calculated by graphing the regions first, always do a sketch, dividing them up where necessary, and then adding up the area of each part. So I've got an example here. Find the area bounded by y equals x squared and y equals x minus 2 all squared and the x-axis. Now, the first thing to do is to sketch it. I know what y equals x squared looks like. That's just my basic old parabola. And this one, on inspection, I can see that a translation has happened. It looks like a basic parabola that's just been moved 2 jumps to the right, or 2 units to the right. So that means it's going to come across here, and instead of going through the origin, it's going to go through here. Now, I can go ahead and graph that in, just getting my basic parabola shape. And that tells me now, if I'm finding an area that's bounded by both of these curves and the x-axis, I must be finding the area that's trapped in here. Okay? Now, I can see that both of these parabolas are exactly the same shape. One's just shifted across. So there's a few different strategies I could use here. I could actually just find the area of half of this bit and then double it, knowing that the other half is going to be the same. Or I could find the area of each of them separately and add them together if I wasn't sure, or if perhaps I was using another parabola for this part. What's going to be important to know though is what is this point here? Because it's the point that's going to cut my region in half. Now, how are you going to go about finding this intersection point? Well, if you've got two curves, how do you find where they intersect? You solve them simultaneously. Now, if y is equal to x squared, but y is also equal to x minus 2 all squared at this intersection point, because don't forget this point here has got an x and a y value that satisfy both of these, then if y is equal to this, but y is also equal to that, then this and that must equal each other at that intersection. So I can go ahead and say x squared must be equal to x minus 2 all squared. Now I need to solve this. So I can expand out the right-hand side. And then I've got x squared on both sides. So basically I'm solving 4x is equal to 4, x must be equal to 1. And that rings true because if I've moved this across 2 and that's 0, and I've got this symmetry here, it makes sense that that would be 1. I could virtually have guessed that, but we're going through the process of solving this in case we get one that doesn't have that symmetry and we need a strategy. So solving the equations simultaneously helps us find intersections of the graphs with each other. Now, this means that I can now say that my area of each part is an integral for the first section from 0 up to 1 of this graph. I need to use y equals x squared dx. And then I'll need to add the other part. Now I can see that the two parts are going to be the same. So I could literally just multiply this whole thing by 2. But what if they weren't the same? Let's use our example and do it in a way that would work if this graph wasn't a parabola with the same symmetry. I'd need to use the second integral, which is from 1 up to 2 of this graph. Now, if you don't like integrating this, we do know how to reverse the chain rule with it, but if you prefer not to integrate that, you can take the expansion and integrate that instead. Might be a little bit easier. So you've got a choice there. There's always lots of ways to do things. Now I use my big brackets here. This is x cubed over 3 between 1 and 0. And I'm going to add it onto x cubed on 3 minus 2x squared, because that differentiates back to minus 4x, plus 4x, and this is between 2 and 1. So now making my substitutions, I've got 1/3 minus 0. That just gives me 1/3 for this whole section. I'm not going to bother writing the minus 0. And for this part, I'm adding, well, subbing in 2 here, I've got 8/3 minus 2 lots of 4, that's 8, plus 2 lots of 4 again, that's 8. And that whole section you could put in brackets if you like, but really there's no chance of making a sign error here, so we should be fine. You don't strictly need them. But we'll need them for the second part because we need to now subtract the subbing in of 1. So we'll need brackets 1/3 minus 2 lots of 1 squared, that's minus 2, plus 4. Now you can reach for your calculator. There's parts you could easily probably do in your head though. Minus 8 and plus 8 is going to go. 1/3 plus 8/3, that's 9/3, which I know is 3. Over here we've got 4 minus 2, that's 2, plus a third, we've got 2 1/3. So we've got 3 minus 2 1/3. I can do that in my head very easily. That gives me an area of 2/3 units square.